Okay, hello everybody. Good morning, good afternoon. Let's give people a couple minutes, 1 or 2 more minutes before we start this webinar. Let's give people 1 or 2 more minutes. We're going to start the webinar soon. All right. I think it is about the time. Let's get started. All right. Good morning, good afternoon, everybody. Welcome to Canon Instruments webinar. We're very happy to have so many people joining us today from around the country and also from different time zones. My name is Terry Chen. I am the Director of Business Development at Canon. Today, we'll be giving a webinar on polymer thermal analysis. Our speaker today is Mr. DiPietro. Dan is the Vice President of Product Management and Applications at Canon Instrument Company. He and his team oversee the product management of the Hitachi Thermal Analysis product line. Before joining Canon, Dan had over 35 years of thermal analysis experience working at TA Instruments. He had held multiple key roles in engineering, production, product management, applications, and also sales. His deep technical expertise, and market knowledge make him a valuable resource for understanding the latest advancement in thermal analysis instrumentation. The title of Dan's presentation today is Real-Time Image Analysis During Thermal Experiments. During Dan's talk, please feel free to ask questions and enter them into the Q&A window. We will be addressing your questions at the end of the webinar. So now I'm going to pass this on to Mr. Dan DiPietro. Dan?
Terry, thank you, and hello, everyone. Thank you for your time. We value your time. As Terry said, I've been at thermal analysis for decades now, and I have to say, at this point in my career, there's not too much that gets me excited anymore. But this subject is exciting to me, and I think at the end you'll find it exciting as well. The ability to look at the imaging of the specimen as it's being analyzed. And I say it's exciting because there's both unique and important implications here that hopefully I can convey. Probably take about 20 minutes, and we'll have time for some questions at the end. You may not be familiar with Canon Instruments. It started back really in the 40s when a professor here in State College, Pennsylvania at Penn State created some manual viscometers that over the years became automated. So today, Canon Instrument is the leading supplier of automated viscometers, as well as some mechanical testing apparatus. Hitachi is the company in Japan that makes the thermal analyzers. As you might imagine, this is a huge footprint in Asia. In Europe, it's very large, but oddly enough, not so much in the United States. And so they've hired us because of our great depth of experience in thermal analysis. And so we've combined forces with Hitachi to provide this alternative to you. I'm going to talk really quite shortly. I expect that most of you know that the role that thermal analysis plays. I think you probably wouldn't be here unless you were already doing thermal analysis. So I probably have just one slide on that. We'll talk about how real view works. And by the way, we coined the term real view. Real view simply means image analysis. And we coined the term real view just for marketing purposes. So when I use the term real view, please think image analysis. And as I said before, the thing that's exciting about this is the coupling of things being unique and important. Sometimes they don't always couple together, and you have some features that aren't so important. So let's start with the role of thermal analysis. You may all know that it consists of a suite of equipment, typically 4 modules: scanning calorimetry, TGA or simultaneous DSC TGA, TMA, and DMA. And these have been staple products in all kinds of physical property testing laboratories really since the 60s. And so these are well established. I think the imaging, again, is not as well established, and so we want to try to illustrate some of those benefits. Again, I won't go into how thermal analysis meets the material characterization needs in a variety of industries, but if you have questions, certainly feel free to raise them. What RealView is 2 types of accessories. The first one is called an observation system. This is a camera and some imaging technology that is for most routine applications, like looking at size of things and changing color of specimens. Kind of a step up would add what we call our polarized microscope. That particular apparatus is even higher resolution and is really well suited to not only measure things like size and color, but also things like crystal growth, which we'll look at. On the left, you see a picture of the DSC furnace. Basically, we have a transparent window in which the camera is shining down into. And towards the right, in the middle of the screen, you see the STA, the specimens there on 2 platforms and looking down. And this technique is applicable to the TGA, STA, DSC, and DMA apparatus that you see on the right. The first example I want to show is a material, cellulose nanocrystal. CNC it's a common filler, actually, and one of its hallmarks is that has some eco-friendly characteristics. It's biodegradable, and what you're seeing on the left in the blue curves is just different loadings by TGA, and you can see 10, 20, 30% loading as well as an unfilled material. And as you look at the pictures on the left, you can see that as a function of loading, the specimen gets more and more yellow. That's the one downside of CNC. It tends to yellow. And as you know, for some applications, that in and of itself could be a problem. What the apparatus does is it has a colored filter array on all of the pixels, so that array can actually report a light signal. And one traditional way of measuring light signal is an LAB scale. So in the case of the L, that's the intensity. In the case of the A, that's a scale that ranges between red and green. And the B scale would be in the positive direction, yellow, and the negative direction would be blue. And so we're looking at the right-hand side of 10% loading. And what we see is we see the B scale, which is an indication of yellowing. And what's interesting about this is I think twofold. One is this is happening well before there's any real thermal degradation. And so, again, certainly there are many applications whereby yellowing would be the definition of performance as opposed to degradation. And therefore, the ability to quantify this on that y-axis scale that you see here is important. It would remove operator error and give instant feedback on performance of things like color stabilizers and antioxidants, things of that sort. And so that's really what's unique, the ability to quantify color and removing the subjectivity as something begins to degrade, oxidize, or decompose. Another example here is similar to it. This is an example of polyethylene. Now these were sheets of material, and what we're plotting here, it's a rather busy slide, so forgive me for that. But you have blue, which is the TGA signal, and you have green, which is the DSC signal, and we're looking at just two different samples. Sample A would be solid line, sample B is dotted line. And you see the temperature program in red. So in this test, this is actually an ASTM method to look at the OIT, the oxidation induction time of a polymer. And so we heat up the specimen and we melt it in the presence of nitrogen. And then at time 0, well, when we're at temperature, we flip over to oxygen. And we see at which point we have this induction time where we deviate from the baseline in an exothermic direction. Very common application. But what's not common really is the ability to see a couple of things here. We see in sample A, we see it yellows rather substantially. So it's beginning to degrade. So in and of itself, that's interesting information. We could have and probably should have plotted the yellow signal here, but the plot was getting very busy. But what's also interesting is that sample B, well, maybe having good thermal, discoloration properties, degradation properties, it doesn't have the same melt strength. Very often this is used in wire and cable, and sometimes they would fill this material with things like talc. It's very common to give it some rigidity in the melt, some stability. And so what's interesting about this slide is, again, being able to quantify color change and also to look at things like stability while you're making, a traditional thermal analysis experiment. Very interesting slide here. This is high density polyethylene. It's a very small specimen, and I know that because when I look at the heat, this is a tiny signal, on the order of maybe 40, maybe 60 microwatts is the total peak height, but plenty sensitive for the Hitachi DSC. That's fine. But what's illustrative about this is we can also plot the intensity of light, and it turns out that when we go through transitions, we can see a darkening of the sample. The apparatus can plot the derivative of that intensity signal, and therefore in the heat signal, I should say in the light signal, you have a proxy for heat. Now, this is no benefit for this particular sample, but what if we were to have a tiny sample within a tiny sample? Again, this is pretty small, but what if we were to have something, that's on the order of micrograms of sample? Well, this next example is a case of, generically we call these fisheye. This could be, unreacted material, could be unmixed material, high molecular weight, something that's contaminating something within a larger matrix. And so this particular specimen, we couldn't get a lot of it, but what we're trying to measure is kind of a speck within a tiny speck, if you will. And when we run that specimen in DSC, we get the green curve. So we can kind of see something that looks fairly predictable here, but it gets a little fuzzy otherwise. Now, it turns out when you run this using the real view, we can actually see the color change. So we can be plotting this derivative of the intensity signal and actually get the result of this particular sample just looking at the color intensity. If you were just to run the contaminant itself, you would get the green curve. This is a 1 milligram sample. The amount of specimen in the matrix is much smaller. But again, looking at light, it really doesn't matter because we're able to kind of decouple heat with light. All we're looking at is color change in this example. So I think this is profound. I think this could be important for people, especially those that are looking at very small samples. Along the same line, this is a packaging material. This is a multi-laminate film that was microtomed and just placed flat in the DSC pan. And you can see the dimensions of this specimen. And so what we're looking at here is the result of the DSC curve of that specimen, that small specimen. And of course, if you run essentially nothing in a DSC, the response will be nothing. And that's what this green curve is showing. But what it's also showing is the light signal. Again, the derivative of light as a proxy for heat flow. And what we also have here in green is the specimen in a much larger mass. So we're just using light to compare with a specimen that is much larger than what you would have, perhaps doing analysis from the field or troubleshooting, some kind of autopsy on a specimen, either in your production plant or from the field. If you look at the video of this, what you're going to see as the curve advances, you can see in green here the temperature going up, and eventually you can start to view maybe this heat flow signal, and you will see which layer is the low melting temperature material. You'll see that center one go dark, indicating that the light has changed. It began to melt, and it melted. And now as we advance on here in temperature, you will see what this particular component, where it's located in the assembly or in the composite. You'll see that go dark now as well. And so the ability for not only to identify small samples, but to identify the location of those components in perhaps a complicated multi-component system is unique. This is this particular example would require the microscope. This is polyvinylidene fluoride, which is often used as among other things. It has many uses, but one of them is as piezoelectric properties. And this particular specimen is mounted on a silicon wafer. And what's interesting about this is the ability to look at things like crystallization and nucleation. I'll play the video and then we'll zoom in on some of these pictures here. So as we cool from the melt, you're going to see that the line darken. And eventually, as you look in the top right, you're going to see the perimeter of the sample begin to crystallize, and then some nucleation sites form, and then crystal structure form as we go from the melt into the solid. If I zoom in on some of these, I can see a few things. First of all, if we were to cool this specimen very rapidly, what we can see is lots of nucleation, but really not enough time to grow large crystals. And that's what's happening here. You see a lot of density of crystallites, and that density increases, but the crystal size increases as the heating rate goes down. And finally, on the opposite end of the spectrum, we have really large crystal sites. So this is also important for those people looking at structure when they're looking at things like nucleation density and size and shape and orientation. So I think that's self-explanatory in that example. The last example is simply using the apparatus as a heating microscope. If I were to start this example, this is using PMMA as an optical fiber. And what we can see as we heat up and we go through these thermal transitions, we see the material becoming more dense, it beginning to shrink and relax. and the software having the ability to actually quantify that, I think is a great advantage. So those are the examples using as a heating microscope. I'll stop there and now open the floor to any questions that you might have. Terry, I'm not able to see the questions. I don't know if you have any questions. I think you might be muted, Terry. Yeah, I'm sorry, I can't hear you.
So we do have one question. We have
Can
a
you
couple
guys-
questions. We can hear you now, Terry. Yes.
Wonderful. Okay. So because I was on mute, that All right. So I think I see a couple questions coming through our Q&A session. So let me read those questions. We will have Dan to address the questions to you guys. All right. So the very first question here is, oh, this is a good question. So can the camera system on Hitachi instruments be used together with the auto sampler?
Oh, yeah, I should have mentioned that. In one case, yes. In the TGA STA, the answer is yes. In the case of DSC, no. The camera and the auto sampler coexist in the case of DSC, but when you're using the camera, you cannot use the auto sampler. It's easy to move the camera out of the way when you do want to go back to the auto sampler. Yeah.
All right, here is the second question. How high a temperature you can go to with the microscope withstand?
Terry, you got to help me on this. I believe it's over the full range, but I could be wrong.
This is the question I cannot give you the answer. For DSC and also for DSC and STA, the highest temperature you can get up to, at the STA, the highest temperature is 1000 degrees Celsius. DSC is up to 400. DMA is up to 600.
Thank you,
Okay,
Terry.
so the next question is, for the color or light signal, can you select certain areas or pixels to analyze it? Or you just, is it the entire frame? Are you analyzing the entire frame or just a certain area or pixel?
It would be the entire frame, but you're able to change the field of view. So you would have to zoom in or zoom out if you see a feature that you're interested in, and be able to look at that composite zoomed in or zoomed out frame. You could not, for instance, be zoomed out and zoom in at a particular location within the field of view. Hopefully that answers your question.
Here, there's another question. There are lots of questions. Do you also have any examples with DMA?
I do. We do, and we can send you those. A couple of things are noteworthy. Some of them, a lot of DMA applications, particularly films, it turns out that you can really chase your tail quite a bit with just the proper mounting, and if there's slack in the sample, if there's wrinkle in the sample, very often you'll see modulus increases because the sample is going slack on one edge and it's not on the other. So the camera helps out there, but there are other ones where you're able to see going from a solid, I should say, amorphous state to a crystalline state as you're bending the sample or pulling it. You can see just the translucence of the sample as you're scattering light as it begins to get more crystalline. So yes, we can send you samples of that as well.
Yes, to follow up with Dan's answer, we do have an application example of using this camera system during a DMA measurement. Specifically, that really helps you to interpret some actually unexpected results. So for example, right after the glass transition, you see a very abnormal increase in modulus. What could be causing it? Is that due to cross-linking, or it is due to cold crystallization? So that application example that Dan is going to send it to you later after this webinar is talking about after the glass transition, you actually see a abnormal modulus increase, which was caused by a cold crystallization. So the reason we draw that conclusion was because you are able to see the sample all of a sudden turns white. That is an indication of the sample undergoing cold crystallization.
Terry,
Okay,
if you
Dan.
would capture that person's name just so we can send that to them, that would be great.
Yes, we have them in this pool. So the next question here is, how does it look like during heat-cool heat cycle? This is, I guess, it's a DSC review.
Yeah, I'm not exactly sure exactly what you mean. I think perhaps what you mean is, can you do heat, cool, heat? Yes, the answer is yes, and probably the way to analyze it. I mean, even without the camera, very often I'll just analyze two heats, right? I want to compare two heats, and I'll probably compare the cooling separately. But what I would do with the camera, and by the way, each particular data point has an image associated with it. So in a heat-cool heat experiment, if you're running it with the camera or the microscope, I would break them up into the respective cycles, and I would do the image analysis kind of separately. You could do it all on one, but it would get really busy, I think, on the screen. But it's easy enough to break up the cycles into the heat, the cool, or the reheat. Hopefully that answers your question.
Just to follow up with Dan's question, answers, I would like to add one more part. So when you do heat-cool heat for a partially crystalline polymer, this is the chance for you to really able to see at what temperature the crystals start to form and at what temperature the crystals start to melt with different heating and cooling rate. And also, you can also quantify the size of the crystals as you're performing heat-cool heat cycle with different conditions. Hopefully that combination answers your questions. So here I have another question. This question is also regarding temperature. There are multiple people interested in being able to see the sample during this temperature, ramp experiment. How high of a T can you go and get good photo? Usually, when you go over 700 to 800 degrees C, material turn to get bright red hot. Can you get good mineral photos at 1,600 degrees C?
Well, what the apparatus goes up to 1,000 degrees C in the case of TGA, and we have no problem getting good picture quality. I would say a typical STA pan, if it's ceramic, would begin to maybe glow red. I don't know, 600, 700, 800 degrees, but we get data all the way up to 1,000 degrees, and we don't have a problem. I don't know for sure, but I suspect the reason for that is the field of view. We're not capturing the pan itself. We're capturing the specimen within the pan. So we haven't had that problem. It sounds like maybe you have had a problem. Maybe you do this yourself, but we haven't had that problem.
This question is really valid. Okay, so I just want to add one more thing here, because Hitachi software, the image analysis software has a capability to do this balance, the color balance adjustment. So you're absolutely right. When you heat up the furnace up to that high temperature, when the temperature is greater than 700-800 degrees, yeah, things will turn hot red. So then using the image actually the lightness ratio adjustment, you can adjust the brightness of that. So you can minimize the red color so that you can still get good resolution. And also our TGA, STA instruments, the maximum temperature is up to 1,500 degrees C. With using the camera system, because the camera could potentially get overheated. So And also with this camera system, we're using a coarse tube. So that's why the highest temperature we're limited to 1000 degrees only. Cannot do anything up to 1000 degrees C. Okay, we have more questions here. So can this system be retrofit for for instrument brands, or is it compatible only with Hitachi instrument?
No, it's just for Hitachi. I'm sorry to say it's these things are built for unique kinds of designs and applications. So it's not designed to fit other apparatus. Sorry, but that's the answer.
Okay, one more question. Do you have to change your objective lens for the microscope for different magnification?
No, I don't believe there's different magnification. You have the ability to put in polarization filters, and that's helpful. And I would go as far as saying it's necessary to look at the crystallization and the structure examples. You want to use the polarized lens, but not magnification. No, it's one magnification.
Yep. And the next question is, how does this relate to optical density?
Ooh, I'm glad you asked that because I have to look this up. I don't know the term optical density. It's interesting. Terry, are you aware of optical density?
That's a good question. I am not very familiar to the
Can you take
definition of optical intensity.
Can you take that person's name? I'd like to reach out and ask them what they mean by that.
Exactly.
That's a new
Yeah.
one.
Let's
Okay.
chat
I'm
afterward.
sorry.
You know, let's
Yeah.
chat afterward. Yeah, yeah. This is an interesting thing. We are able to quantify the lightness density, the lightness. The optical density, I don't know what is the definition for that. But in one of Dan's presentation slides, he shows the L signal. The L is the lightness. I don't know if that is the optical density. I'm not sure. Okay, so the next question here is, are you able to access the raw data from the image signal to do offline analysis or export it as a video?
Oh, sure. Yeah, I mean, if the question is the raw data in the shape of a video, yes, and also the raw data in the form of an Excel file. So again, I think what's unique about our machine is that you have the ability to look at things like LAB as signals, and as such, they exist in the data file that you can most certainly export. So you could export the picture, the video, the raw data in Excel format if that's what you're looking for. Hopefully that answers it.
All right, so I think we are over the time for like half an hour, 30 minutes. If you have any additional questions, please feel free to continuously enter those in the Q&A session. We will address your further questions via email. And you have Dan's email from the presentation, so always feel free to reach out to us if you have any additional questions. So we will be more than happy to work with you and help you with your research. With that, we're going to close our today's webinar. Thank you very much for everybody. Thank you for your attention.
Thank you.